And then we'll move to the full language that I really want to consider, which is call by push value with type recursion. Okay, so it's two parts. So I put as much as possible into the PCF part so that we can kind of do it in an easy setting, right? So numbered recursion is a language feature, if you like, something you can put into a language, but it's just equivalent to ordinary recursions in a certain sense, which you'll see. When you see what it is, I fear that you'll say, oh, is that all it was, right? And people just use it all the time, just didn't give it a name, right? Well, so what I'm doing is giving a name to something you've probably already seen. But by putting it into the language explicitly, we'll see how this leads to easy proofs of properties that we know how to prove by other means. So it's new proofs of old theorems, which have certain advantages. And actually, when I say the proof of syntactic continuity becomes a lot easier than it was before, I think that's true. When I say the proof of adequacy become easier than they were before, you might say that claim is a bit questionable. So when I say that these proofs are easy, what I mean is that we can do all the hard work just in the operational semantics and get it out of the way before we come to the denotational semantics. So it's a syntactic theory, but we still do have to do hard work. I wouldn't say that the overall amount of work is reduced. It's just that you're doing it in a different place before you think about denotational semantics. And I kind of know from experience that many people find operational stories more accessible, so they'd rather do the hard work there before getting to the denotational part of the story. And there has been similar work in the past, and one of them was even presented in LFCS seminar in the 90s, where Ralph Loader, I don't know if anybody here was present. Nothing. Okay, so you heard Ralph Loader talking about elementary proofs of adequacy. And I think this is a bit simpler, but it's the same. It's not so a million miles away. Okay, so just for some background, this is PCF. So I can use the mouse to point, but it's not in a. Actually, it'd be helpful if I move the mouse around a bit and probably make it worse. No, that's better. Right. Okay. So, right. This is PCF, invented in Edinburgh. Is that right? By Gordon Plotkin. And so it's just, well, I'll leave out the number types. So that was the main point at the time. But for the purpose of this talk, it doesn't really matter. We'll just have booleans and function type, and lambda calculus, and conditionals, and recursion. Right? Just term level recursion, no type recursion. And we have call by name evaluation. So this means M evaluates to T, and you define this inductively in a call by name way. And you evaluate a term, in a closed term, into a terminal, which would be true or false or a lambda abstraction. That's PCF. Okay, so these definitions are very commonly seen. So first, oh, sorry, right. Now, different versions of this talk will be in, okay, so this is the first typo of the day. So just see recxx, okay? Because this wasn't called by push value, this is just called by name now, so there shouldn't be forced there. So omega is just a term that diverges, just runs forever. This could be at any type, okay? And now recursion has these approximants. So you say the 0th approximant is just omega, and the approximant m+1, you just substitute. Okay, so this is all definable within PCF. At the moment, we're not changing the language at all. And now here are some properties that you can see in the literature. They're kind of obvious properties, monotonicity and continuity. So one of them says, if you see as a program context, right? So let's say it's got Boolean type, but there's a hole. The hole could appear several times. So if the context applied to diverge actually runs and gives you a number, then if you replace that diverge with a term, you're still going to get that number, right? Because obviously it didn't use this part at all anyway, so it doesn't really make any difference. So that's monotonicity. That's easier than this second part. Second part says, if a recursion, oh, missing close square brackets, there and there, second and third typo of the day. If that gives you an answer, then there's a K, not n. This n and this n are different, right? Okay, there's a k such that the kth approximant also gives you the answer n. Right, so this is, again, it's a pretty obvious fact, because if this happened, then you had to unwind this recursion, and you did it, let's say, I don't know, some number of times, 1,000,000 times. So if you set k to be 1,000,000, that will be good enough. That's the intuition. And you would think this would be easy to prove, but actually the proofs in the literature, well, the ones actually, there may be other proofs, I'm not sure I've found all of them, but the ones by Pitts and Lassen are surprisingly complicated for the continuity. I'm not saying for the monotonicity, but for this one, they're surprisingly complicated, because you can't just prove it by induction on this, right? This is only for thick derivations of ground type. You need a more general statement for derivations of other type. Somehow you're going to have to talk about this thing involving having some proximant, and the k's are going to split into different cases. It starts to get complicated. Yeah. Oh, if you think of an order, so big omega is below m. It comes. I mean, it's inspired. The terminology is inspired by domain theory. So it's saying that the context is like a monotone function from, bottom is at the least of a domain.
You repeat the question.
Oh, sorry. Right. The question was, why was monotonicity here called monotonicity? Right, okay, I knew I had to repeat the question from the remote people, but I didn't realize I also had to repeat questions from the audience. I can do that, that's no problem. Right, so everyone is on the same page. And right, so the idea is that big omega is like the least thing, and so that's less than m, so therefore the result of this thing has to be bigger than the result of this thing, but this is ground type, so the only possibilities are divergence or a number. The only thing bigger than, greater than or equal to returning n is returning n. So it's a kind of monotonicity in that sense. And in the same way, this is a kind of like the continuity that you get in domain theory. Thanks for the question. Right, before we carry on, I have to introduce you to this not very complicated idea called extended natural numbers. So an extended natural number is either a natural number or omega, which is bigger than all the others. And and every extended natural number has a successor, which if that is an actual number, then you just add 1. And if it's omega, you stay put. You would probably guess that if I didn't tell you, which means that every extended natural number can be uniquely expressed as either 0 or a successor. Very exciting. Right, anyway, so what is numbered recursion? It simply means that we add to the language this facility to annotate. So instead of, we extend the syntax, that's not correct. We replace the typing rule, we get rid of, in numbered recursion, we don't have rec anymore. Instead of that, whenever we have rec, we annotate it with an extended natural number, explicitly in the syntax. Like I say, lots of people have done this. It's really just a different syntactic choice. It's a very minor thing. So what is now we have to extend the operational semantics. So how do we evaluate this thing? If n is 0, we diverge. Again, that space is another typo. That should be we, in case you can't guess. And if it's a successor, you unwind it. So one thing I should have said is that this operational semantics, which in fact the operational semantics from we had previously is called unwinding semantics. When you see recursion, you unwind, which means that if you have omega here, what do? You're just unwinding it and you're going to get another omega. So it's just an extension of what we had before, right? Again, I'm deliberately doing lots of things simply in the PCF setting because it gets more complicated when we move to the second half of the talk. So I think it's good to do it in a simple setting. So the language with recursion embeds in the language with numbered recursion. How does that work? You just annotate all the recs with omega. You annotate everything with omega. And this is an embedding, or to be more precise, it's a functional bisimulation, which we can call an embedding. So if M evaluates to T, then its translation evaluates, and if its translation evaluates, then S must be the translation of a term, right? So that's saying that this is a function, this embed, we have a functional by simulation from the language with recursion to the language with numbered recursion. So that is the first of our list of results, right? There's going to be a list of about 8 quite similar results. So I have to kind of, you have to kind of keep track, because otherwise the results start to look a bit samey, right? Okay, so for this language with numbered recursion, remember we have this operational semantics, which we're calling the unwinding evaluation. And I'm going to write less than or equal to for the order given by these annotations. So this means that they're the same term, except the annotations on this are allowed to be bigger than those, okay? Probably pretty much what you would guess. And then this is something that we can prove just by induction. If we have a smaller term and a bigger term, and the smaller term evaluates, then the bigger term evaluates to something bigger, right? Again, not a surprise, but this is, so there's going to be about 4 different monotonicity statements. So I'm just, and they're all kind of unsurprising, right? But it's just important to keep track. We also have correspondingly a continuity statement. So I need to talk about approximant. Approximant of a term is a term where, first of all, there are no, it's less than or equal to it. You're not allowed to have any omegas, and okay, in the language that I've given you, all the syntax is finitary, so this second condition doesn't matter. But if you happen to have some infinitary stuff in the language, which is something I like to have, we'll see that later, then you need to add this extra bit. These annotations all have to be 0, except for finitely many of them, right? So that's what an approximant of a term is. So now we can state continuity of evaluation, which says that if you have any evaluation and you have an approximant of t, then there's an approximant of m that evaluates to something which is at least this other approximant. So that's continuity. From this, now, okay, so the nice thing, so what's the big deal with numbered recursion? It's just such a simple syntactic thing. It enables you to state these kind of statements, and you can easily deduce this other statement from this one, the one that we saw before, from this one. So you don't need that complicated proof anymore. You can just do it this way. So this actually, this is just, I mean, this continuity of evaluation, you have to first prove that substitution is continuous, and that's about it. That's pretty much all. It's quite easy to prove. Generally, this is a convenient way of thinking about continuity. You know, what if something, you have a function, you get an answer, then you have an approximant of the answer, there's some approximant of the input. You know, any approximant of the output can be obtained from some approximant of the input. That's like some of it. Okay, so far, what do we see? We've seen the small language with recursion, with its unwinding evaluation, and then we saw a big language with numbered recursion, with its unwinding evaluation. We saw the properties of unwinding evaluation. Now I want to move to a different evaluation, which is called the decreasing one. So we change the interpreter, we just make one change. The new rule says that when we evaluate rec n x, we don't have this whole case analysis of 0 and successor. We choose a smaller number and evaluate, and ignore the thunk, right? For this part of the talk, the thunk isn't there. And evaluate, you do the unwinding only with m, so it's getting smaller. Now, the case that there are a couple of cases that matter here. The big one is omega, right? Previously, with omega, you unwind it, you've still got an omega. But now, you're choosing a number. So everything has become non-deterministic, right? This is a countably non-deterministic interpreter, so that's a big change. Secondly, I have to emphasize this. At any time, this interpreter has another change that we have to make to the interpreter, although maybe you could say it was already there, but let's, now we have to be clear about this, that at any time during evaluation, you're allowed to die. That really matters in the case that n is 0, because then you have to choose a number less than 0, which obviously you can't do. So dying is the only option when faced with this instruction, right? So So, right. So you've got countable non-determinism, and you always have the option of death. Yeah.
It's not deterministic, but all the changes with the numbers on the regs, right?
Yes. Okay. That's right. It's a very special kind of, yeah, it's a very special kind of non-determinism. Yeah, I need to emphasize that. Yes. But that's it. That's the, so we've got two different ways of evaluating a language with numbered recursion. We've got the unwinding interpreter and we've got the decreasing interpreter. And we use the word, when we talk about termination, that means that our process of evaluation either returns or dies, right? Either of those outcomes is called termination. Okay, so we want to, at the moment we've just worked with interpreters, right? But it's convenient to have big step relations when we're talking about evaluation. So for the unwinding interpreter, the deterministic one, we just have a relation like this, which says M evaluates to T, and that's inductively defined. Now, so the decreasing interpreter, which is non-deterministic in a special case. Now, people studied a big step semantics for non-deterministic languages. People like Soren Lassen studied this. And so what they did was they had two inductively defined judgments. They have this judgment saying that M may evaluate to T. And they had another judgment. This one means M must terminate and T is the set of all things that can be returned. Right? So, and again, this is defined inductively. I'm not saying these are the only options. You could do this first and then you could put less here and use that to that. But if you want to treat them separately, then this is a good way to do it. Yeah.
Is everything in T must be returned by something? Or is it...
Yes, T is the set of all possible returns, yeah, and nothing else. It's that, yes. So, right, T is, yeah, the things that may be returned and only those things. This is intended to be, a function, or at least a partial function, right? So this is part of the general theory of relational reasoning for languages with non-determinism, these two relations. It's not specific to this talk. It's not specific to numbered recursion. And each of these relations, this one for the deterministic language and these two for the non-deterministic language, they're all defined inductively. Okay, so now we're going to get more variations. This is where I have to kind of go. So we've seen these properties. We see properties monotonicity and continuity for evaluation with the decreasing interpreter. So with the unwinding interpreter. Now we're working on now we're in the world of decreasing may evaluation. So here's some terminology that is quite useful for this story. So a semi-directed poset means that any two elements have an upper bound. So it could be directed, but it could also be empty, right? The empty set is not directed, but it is semi-directed. Okay, so this is a useful terminology. And the first thing we could prove is that may evaluation is semi-directed, meaning that if I have two terms with an upper bound, and I manage to, and I get something out of these two terms, so M may evaluate to T and M prime may evaluate to T prime, oh, this should be diamond here, right? And M double prime may evaluate to some upper bound of these two, right? So there's a missing diamond. Okay, and what about, so what this is actually equivalent to a combination of two statements. First of all, saying that we have upwards monotonicity for may evaluation, and secondly, saying that the set of things that you may evaluate to is semi-directed. Right, those two things together are equivalent to this, but this way is convenient for proving, right? You just do it by induction. And secondly, we have continuity. So if M may evaluate to T, and you have an approximant of T, then you have an approximant of M that gives rise to something bigger than that approximant. So you have semi-directedness and you have continuity. So these are the properties. I'm just kind of systematically going through the properties in a deliberately easy setting before we get, so that that's out of the way before we get to the complicated setting, which is probably what I should have done with the paper. Anyway, never mind that. Now there's a missing backslash, and okay, So we haven't got to the must part yet. I'll come to that next. But already I want to connect the unwinding and the decreasing way, because a lot, the whole adequacy theory, these two results are crucial for the proof of adequacy. The relation between unwinding and decreasing. So this one says, if you've got this below this one, if the lower one may evaluate, then the in the decreasing world, then the upper one does evaluate in the unwinding world. And conversely, if you have something which evaluates in the unwinding world and you have an approximant to the outcome, then in the decreasing may evaluation world, you can get that from an approximant of the input, right? Again, nothing here is surprising and everything is just proved by induction on the derivation. Okay, now we come to must evaluation. What properties do we have here? The first thing we have, okay, so first of all, I need to tell you about the lower preorder. Generally, if you have a poset and you talk about subsets of that poset, you have a preorder between those subsets. It's called the lower preorder, which means for every element of this, there's a smaller element of that. The lower preorder. Have I? I want to say that the lower set of this is going to. I've got a horrible feeling I'm this the wrong way around.
Is that the lower Egg-Milner?
No, Egg-Milner is when you have both together, both directions.
Oh, upper and lower.
Upper and lower.
Yes.
Right. Egg-Milner is convex. I've got a horrible feeling this is the wrong way around. There's also a backslash missing on in, but that's the least of my problems. I think this should be the other way around. Yeah, I think it is. I think I've got this back to front. Sorry, I think this is the upper one. Right, I think it should say for any S in big S, there's a T in big T such that S is less or equal to T. Right. Yeah, it has to be. Because the empty thing should be lower in everything. Right. Okay. So now we have, so for what about the must evaluation? We have downwards monotonicity. So if I have the bigger thing evaluates, and then a smaller thing is going to evaluate to something which is below it in the lower ordering. And then finally, well, this is certainly what we want. This one is just a general property of the relationship between must and may evaluation for a non-deterministic language, right? This is not specific to our story. This just says that if M must evaluate T, then T is precisely the set of things that M may evaluate. But remember, this is saying more. This is saying that M must terminate, right? That evaluation must terminate. This is what this judgment is designed to say. And then the last property, and the big one, is that the must, and this is specific to our setting, is that must evaluation is total, right? This process of the decreasing interpreter. So we had the unwinding interpreter, which is partial, it can run forever, but it's deterministic. And we replaced that. I suppose I don't need to wear this amazing black glove anymore since I'm not using the tablet, although I think it's so stylish that I'm going to wear it anyway. We've also got the decreasing semantics, which is non-deterministic, but total. Why is it total? Oh, I don't know why informally. I think the whole of informally should be in red and not just the first letter. The reason that this thing terminates is that you can see this as being a special kind of, if you could translate this into a language with countable non-determinism and and no recursion. So it's like it's one way of thinking about this is you're expressing recursion, you're converting it into a non-deterministic choice. Non-deterministic choice in itself is not going to cause divergence, right? If I just take lambda calculus and add countable non-determinism and that's not going to cause anything to run forever, right? So it's just the usual argument why evaluation of lambda calculus terminates. So it's not at all surprising that the decreasing interpreter is always going to terminate, and that makes must evaluation a total relation. Okay, so that's, if you like, the end of the operational story for PCF. We've seen all the properties. And now we can start, we've seen the monotonicity and continuity, they're all straightforward, right? I said now we're going to talk about denotational semantics and adequacy. So, a computation type B, which shouldn't be underlined for this part of the talk. Okay, so now we have a quick change of subject to denotational semantics, which is probably a bit too fast if you've never seen any of this before. The idea is that every type denotes something like it will be a poset, certain kind of poset. It's got to have a least element, and every increasing chain has to have a supremum. And this is a way of interpreting recursion. Any term denotes a continuous function. Continuous means that it preserves the supremum of these chains, not necessarily preserving the least element. And the way that you interpret these approximants to recursion is by applying, you take the denotation of M, which is a function in a given environment, and you apply it to the least element that number of times. So that's exactly what, if you're used to denotational semantics, that's exactly what you would expect this thing to denote. Right. So, typically we define a denotational semantics and we want to prove that it's adequate, right? We want to prove that the denotational semantics agrees with the operational semantics. Now, sometimes people only consider adequacy at the ground type. I would have considered adequacy at all types, and this is one way of saying it. So when we're evaluating a closed term, M of type B, ignore the underline, adequacy says that the denotation of M is the supremum of the denotation of all the things it can evaluate to. And what does this mean? Unpacking it. Well, if M does evaluate to something, that just means that the meaning of M is the same as the meaning of the thing it evaluates to. And if M runs forever, this set will be empty, and this will just say that the meaning of M is the empty, is bottom. Right, so it's saying that if you evaluate, you preserve denotation, and if you run forever, then the denotation is bottom. The set of things that M evaluates to is semi-directed, right? In fact, okay. So how do we prove this? So there's a traditional way of proving this, which is by logical relations. But now we have a really easy way of proving it. We can simply prove it by induction. We just say that if M must evaluate to T, then the meaning of M is the join. Now, remember that this thing is semi-directed, right? So, and we have in any CPPO, I should say this, we are countable semi-directed. In any CPPO, we have any countable semi-directed subset has a supremum. So this supremum exists, and we just proved by induction that the meaning of M is the least upper bound of all of these things in T. And this least upper bound is the same as this least upper bound. Why? Because remember the relationship between decreasing and unwinding evaluation. We said that if anything you can get from decreasing, you can get something bigger from unwinding, and conversely, anything you can get from unwinding, you can get an approximant from decreasing. So that means that these two semi-directed sets are cofinal, and therefore they have the same supremum. So it's just a simple induction. We don't need a logical relation. So we did all the hard work before we started thinking about denotational semantics. It wasn't that hard work, but it was, we had to prove totality. That was the hardest thing. It's as difficult as proving that simply typed lambda calculus evaluates totally, right? So that was what we had to do. Of course, language with recursion isn't total, but when we have numbered recursion and we have the decreasing interpreter, it is total. So that, if you like, is the end of the first part of the talk. Yes?
When you prove totality, then did you use logical relations there?
Okay, so the question from Ohad is, when we prove totality, did we use a logical relation? We use a logical predicate. Yeah, indeed, we're using, yes. So we're still using, we're using the method of logical predicates. We're not using logical relations. I should say for PCF specifically, I think there is an old proof of Plotkin that does just use logical predicates rather than logical relations. So, but anyway, so much of the stuff that I've talked about so far has come up again and again in the literature in different forms. I'm just bringing stuff together. It might help if I actually knew all the references to cite properly, but this is just so, this concept of numbered recursion has popped up so often But so I'm just like laying everything out in a systematic way so that then we're in a good position to move forward. Okay, so now for the second part of the talk, so we're supposed to finish at midday, including questions, is that?
More or less.
Yeah, okay. So, right, hopefully this will. So, very briefly, for those of you who were at the general meeting yesterday, or in any case, those of you who weren't at the Huawei meeting yesterday, I'm assuming that's a bigger group, that nobody went to both. So, what is it? It's a calculus that has call by value and call by name together, and you have values and computations where values have value type, computations have computation type. And here is the syntax of types. These are the value types, so you have things like sum. Here are the computation types, you have things like function types. The green bit is which is infinitary, that's an optional extra. Ignore that if you don't like those things. But importantly, you have U and F. U is the type of thunks, and FA is a type of computations that are trying to return a value. Okay, that's a quick summary of call by push value. And we need the, not quite, we need the interpreter. So when you're evaluating a term, you evaluate to a terminal, and the terminal is either return a value or a lambda abstraction, one kind or another. Here's the interpreter. There's all the different cases, but let's say when you're returning something you have to return, and then you have sequencing. So this means evaluate M, and then if you get an answer out, evaluate N. Lambda abstract application is what you think it would be, and you force a thunk in the obvious way, and that's it really. You don't need to spend any more time on that. So that's call by push value. Okay, but now I want to extend it with type recursion, right? So I don't just want to, I mean, I've grown the language from PCF to call by push value with term recursion, but I want to go further and have type recursion. So we have recursive value type and also recursive computation types. By the way, call by name, so when you translate call by value into call by push value, the call by value type translates into a value type, and the call by name type translates into a call by name type. So we want both kinds of recursive types in order to subsume, you know, call by value with recursive types and call by name with recursive types. And also, let me say, I mean, some of you may have heard of this terminology, equirecursive type versus isorecursive type. So these are isorecursive type, meaning that you explicitly use fold and unfold to move, or maybe you prefer the word roll and unroll or something else. We're moving between the recursive type and the unwinding of it, right? This is not fold in the sense of functional programming, so be careful. Also, let me point out that we have open types here, right? Types can have free variables, but the term syntax only uses closed types. So it's not like polymorphism where the term syntax uses open types. With recursive types, it's much simpler. Only closed types are used in the term syntax. Right. So what I want to do, I think probably the best order to do this. Okay, I'm only going to give, I'm not going to go through all the details of this, which would be another 20, take me another 5 talks or whatever. I'm just going to go through a few details and hopefully enough to give you some flavor of what the difficulties are and how we deal with them, okay? I mean, the point is to make the whole story that we've told in the first part of the talk go through for this language. Of course, the challenge is not the call by push value, the challenge is the recursive types. So first of all, we have to extend the denotational semantics. So for recursive types, there's a traditional difficulty that you have open types with type variables that occur positively and negatively. So we can't just say type denotes a functor, it's not so simple. The solution is to be found in the famous paper of Plotkin. And the idea is you start with either a category of CPO and partial continuous maps or CPPO and strict continuous maps. And that's your category D. And then you use these things called embedding projections, which is like a way of growing a CPO. And so the open, even though a type is mixed variance, it's still covariant in these embedding projections. That's the basic idea. Again, I can't give you an introduction to this if you've not seen it before, but so sorry about that. So we want to extend the syntax. So the first thing we need is to talk about a cap on a type. A cap of a type means that you annotate each rec in the type syntax with an extended number. So obviously, the set of caps on A is ordered. It has, oh, that should be a wedge, not an intersection, sorry. It has binary meets, and there's a top cap, which just means that we're writing omegas everywhere. Okay, and here's what we want to say. Oh, by the way, there's a backslash there before the beta, right? So on a closed type, we want every cap to denote an endomap. So if A is a value type, then this will be a partial continuous endomap. If A is a computation type, it will be a strict continuous endomap, right? But in each case, it's an endomap. And if alpha is below this, okay, what are the basic properties? First of all, it should be monotone. The semantics of caps should be monotone. Secondly, the meet of two caps should denote the composite. And of course, that means you can infer very quickly that it should also be the composite the other way, right? Beta composed with alpha. So although in general, endomaps don't commute, the particular endomaps that we're using are going to commute, right? And finally, we want this thing, the top cap, should denote the identity. These are the three basic properties. This is what makes everything work. But of course, this is only for closed types. We have to deal with open types to give a denotational semantics. So let me now try and go off onto open types. Let me just say briefly. So we want to say, if we've got an open type with a single free variable, let's say, intuitively, it sends CPOs to CPOs, it sends embedding projections to embedding projections, and it should also send endomaps to endomaps. Now, if we knew that A was covariant, then we would expect the endomap part to preserve composition. But the problem is, it's not, it's mixed variance. So that's not going to work. So how are we going to set this up? One thing that you find in the literature is that people will do a whole thing with mixed, you have a negative part and a positive part, and I find that totally confusing, especially when you get mixed recursion, nested recursions. I find that too complicated and not very intuitive at all, because after all, it's just a type involving X. It's the same X. It's not like it has one meaning when it's negative and one meaning when it's positive. So I'm really trying to get away from that. So here's an alternative thought. Which alternative approach, which is not, actually, this is not just specific to this story, but generally for the semantics of recursive types. So if we have the endomaps on a CPPO form an ordered monoid, actually a CPPO monoid, right? Now, if you have an ordered monoid, you have a preorder. Okay, I'm going to have to explain what I mean here. So for two lists of elements, we say that this list is below that list, when that means the composite of everything in S is below the composite of T, but also the composite of the reverse is less or equal to the composite of the reverse, right? So that's the reversible preorder. So that means the composite is below that, but also when you reverse it, it's below. So this is a relation on lists, and if you have a mixed variance function on monoids, you're not going to preserve the composition, but you are going to preserve the reversible preorder, right? So this is convenient. So this is what we want generally. We can set up our semantics and just require preservation of the reversible preorder. And to make it a little bit more abstract, we can say that a CPPO reversoid means, we do this with post sets, I'm doing it with CPPOs, right? You would have a preorder on, let's say, non-empty list. We don't need to worry about the empty list because we've got an identity element, new, and an element newt. And what do we want to say? That on singleton lists, it corresponds to the order. That if we have two relations, then we can concatenate. Oh, I missed out the print rule that says if S is below T, then the reverse of S is below the reverse of T. Right? That's another one we want. And we've got a neutral element and bottom, composition with bottom, it gives you bottom. So if you've got a CPPO monoid, you can forget the composition and just think about the reversible preorder, that'll give you a CPPO reversoid. So this generally is a way to set up. So this category of CEP is not just a category, you also have this like reversoid of endomaps associated with each object. And so what's an open map going to do? It's going to send objects to objects, maps to maps, and these caps to caps, and everything is preserved. So that's the basic idea. This is how we deal with mixed variants. As I say, this is not specific to the theory of numbered recursion. This is just a useful thing for general. There's more I could say, but that would go off in a different direction. So, right. Okay, so that's roughly how we organize the semantics of open types. We now have the semantics of caps. We can use all this to get a semantics of caps, given with the properties we want. Right. So now I need to change the language. So I've said that we want a term syntax with numbered recursion. That means that every occurrence of so that means term recursion has to be annotated, just like in the first part of the talk. But also, every occurrence of thunk has to be annotated by a cap. That's the big change. Thunks are annotated. And what does this mean denotationally? Remember that beta denotes an endomap, so we're just applying that endomap, like a strict endomap. Okay, so we need unwinding interpreter and we need decreasing interpreter. So it comes in various parts. So this is where we have different. So the first part of the interpreter is that we're going to evaluate a capped closed value. So that means a closed value together with a cap, and that's going to evaluate to a value, right? And that process of evaluation could diverge. It's not surprising. Remember that alpha denotes a partial endomap. So because it's partial, it's not surprising that this thing could cause it to diverge. That's the first part of the interpreter. The second part is actually three things simultaneously. So you've got a closed computation of F type evaluates to a value. That's called complete evaluation. An ordinary closed computation doesn't evaluate to a terminal, it evaluates to a capped terminal. And a capped closed computation also evaluates to a capped terminal, which is with a lower cap than this is beta low alpha. All right, and this is all, this is all pulled out of a hat. And to be honest, there may be other ways of doing this, but this does have all the properties that we want. Above all, the totality, which is the big one, right? So here are some example clauses. This is from the first part of the interpreter, right? To evaluate a folded value, we look at n and either it's 0 or it's a successor, and we behave accordingly. To evaluate for thunk, we just evaluate m cap. Remember that thunk has a cap associated to it. To evaluate an application, we're going to get something out with a terminal with a cap. That we then know to evaluate the value on the specified cap. And then finally, we're evaluating beta. So these rules, once you know the form of the rules, they're kind of the only reasonable thing we could have. For an unfold, so this is recursive value types. This is for recursive computation type. So to evaluate unfold, we first of all evaluate m to a fold. That's going to give us a number, and then we do something different depending on whether the number is 0 or successful, right? So these are example clauses from the unwinding interpreter. For the decreasing interpreter, I'm going to show you the corresponding clause. All we've done is just take these two clauses and just replace the unwinding with decreasing, right? We just choose here at this stage, we just choose m less than n and carry on. So we just systematically change the unwinding to decreasing, right, by replacing the appropriate part. Okay, so pretty much the rest of the story is the same as for PCF. There are a few extra statements you can say about, for example, if you have a value and you evaluate it with a alpha. Well, anyway, you've got some extra properties, but they're all straightforward. But the big challenge, like the centerpiece of this story, is showing that evaluation of the decreasing interpreter is actually terminating. So in other words, that must evaluation is total. And so for that purpose, the real crucial. So normally, you define totality with reducibility predicates, right? Terms are closed terms are reducible. You define that by induction on types. Here it's more subtle. The poset of types with caps has a well-founded relation. You have to construct the well-founded relation, and everything is defined by recursion over that relation. So that's the idea. And actually, to make this work, we have to set up a whole theory of well-founded relations on a poset, which is quite interesting in its own right. But that's another story. So yeah. So and you have the value types being kind of covariant and the computation types being contravariant in a certain sense. And I should say, by the way, I think I didn't mention this, that part of this work was done, we should have this slide. Part of this work was done in collaboration with Marco de Vesa's campus, especially this idea of how these reducibility predicates were defined, which is really some key part. Okay, so we're kind of running out of time, but we're also on the last slide, so that's a quite happy coincidence. Looking at term level, numbered recursion is really nothing more than an alternative notation. We're just writing numbers, but we can easily macro expand that and say, we can say that it's convenient to make it explicit in part of the language, but it's easy to see how to translate back. We're certainly not adding anything to the language in a genuine sense. For type level, the way I set it up, it looks like a genuine extension, but in fact, you certainly can, even with all these caps on recursive types, you can translate back. You have to associate to each alpha. The endomap that it denotes can be expressed by a term. So you can do a syntactic translation backwards that preserves denotational semantics. It doesn't preserve operational semantics in a straightforward sense. I mean, complete evaluation would be preserved, but that's the kind of the one that really matters, where you get that value out. But the other evaluation would not be preserved in any reasonable sense. And I'm not saying that this way of doing the interpretive is the only thing that makes this work. It's just what we managed to make work. So looking to future work, I mean, there have been problems in the past with the traditional proof of adequacy uses logical relations. And this is quite problematic in effectful situations. And there's a paper by Plotkin and Power where they used a different method, which is somewhat related to this, for proving adequacy, not with type recursion, but with term recursion for call by value that they were working. So I'm hopeful that this proof of adequacy, this approach to proving adequacy, is useful in effectful situations. However, there is one thing that I'm not at all happy with, which is this adequacy proof really uses the fact that everything in the model is continuous. And there are also models of interest where things are not continuous, for example, where things are not continuous. This often comes up when we're working with countable non-determinism. You relax continuity to omega-1 continuity. You can imagine, let's say, for example, you're doing the model of, you can just take the model of PCF, where you have all omega-1 joins, not just omega joins, but also omega-1 joins, and the functions are just omega-1 continuous. That is adequate. The logical relations argument works. This argument doesn't work. So it's a bit unfortunate. We seem to have a proof of adequacy which is more powerful, which may be more powerful in some settings, but then the traditional logical relation proof, which is also, you need a lot of work to make that work with recursive types, but that's another story, is more powerful in other cases. So I'm not amazingly happy with where we've ended up. I would love to be able to adapt this proof to, the omega-1 continuous setting. Totality is easy, you can make it, make everything, you can make the ordinals go up to omega-1 and still prove that everything is going to terminate. The problem is that just showing the last part, even for term recursion, right? Just this part here, where we prove inductively that if M must evaluate to T, then the meaning of M is the join of all the things it goes. Simple induction relies on the model being continuous, right? This set is semi-directed, and this model is continuous, and those two facts go together. And I can't see how to do that for a non-continuous model. So that's the difficult part, not the totality. That would be fine for the omega-1 setting. Right, so that's kind of where we're up to. So it's progress, and it's helpful for, I believe it will be helpful for effectful things. And it has the advantage of pushing all of the hard work into the operational semantics before you even start to think about denotational semantics. But it only seems to work for continuous semantics, and that is a pain. It's not the only example of a piece of theory that's been developed for continuous setting that doesn't obviously adapt to omega-1 continuous. I can think of other, this phenomenon has hit us in the past in other places. And that's it.
What about polymorphism? Since you were here, you're giving me filter types. Yes, part of the job is done.
Okay, so Giulio asked, what about polymorphism? So I actually think that this is good for polymorphism. I haven't worked through the details, but I had an earlier paper with Marco on, it was like a syntactic approach to proving adequacy. It was just for term level. And that in that case, we were able to deal with polymorphic types like universal polymorphic types, but not existential. This story, I think, will be fine. I think if you add polymorphism and existential, you'll still be able to prove all the totality, but the proof of totality will be more complicated. I mean, it will be as difficult as, obviously you have to prove everything implicatively in the usual way. So it'll be at least as hard as proving termination, of a language polymorphism. But I think we can do that. And then if you have a model with polymorphism, you will just be able to prove it by, assuming it's continuous, you should just be able to prove it by induction. So I think this is actually pretty good for polymorphism. And it has the advantage, I mean, for polymorphism, designing a model is more difficult. So it's nice to get all the hard adequacy stuff out of the way before we have to worry about denotational semantics. So yeah, I haven't worked through the details, but I think I should say that it's true that we have open types here, but in type recursive language, open types are just used for building the types, but the term syntax doesn't use open types, like I said. So in that sense, we only, the work that we did to define the reducibility predicates using this well-founded relation definitely is only working with closed types. So, so it is definitely more work to make this work. Let's put polymorphism. There might be, so it would be natural, if we were going to extend this proof of totality, then it would be natural to think of an open type as having two zones, like the variables that are used for polymorphism and the variables that are used for recursion. But it may be that we could actually do a different proof to show that a different way of constructing the reducibility predicates that combines them all together. That might also be possible. But yeah, in any case, I'm definitely confident that we can make this story work for polymorphism, including existentials, where we had a problem before. There's a good question. Yeah, it's really a strength of this system, I think, potential strength. Yeah.
I have a question. What's the relationship with step indexing?
I didn't hear you.
Step indexing.
Oh, okay, right. So the basic answer. So okay, repeat. So Ohad said, "What's the connection to step indexing?" So everything that I've said is about general recursion and models of general recursion using domains, right? There's a whole world of guarded recursion and models of guarded recursion using either metric spaces or topos of trees, and this connects in some way that I don't really understand to step indexing, but other people do. And I don't know any of the relationships. I mean, it's true that they use numbers and we use numbers. That's quite a small connection. But I mean, it would be very nice if, for example, remember how I said that the termination, in the case of language with term recursion, the termination can be seen as a consequence of the fact that a language with countable non-determinism terminates, right? So you don't actually need to prove anything more than that. It would be nice to have a similar high-level view for the type recursion, because at the moment we don't. We have this quite custom designed proof of termination. It's not the case in any way that I understand that this with type recursion that you can sort of translate it into a language with what? Some kind of recursive types where everything terminates. People in the guarded recursive world, they have such a thing, right? They have recursive types, but they guarded recursive in a special way that makes sure that everything terminates in a certain sense. So there may be a connection, and I certainly would like to understand that, but that definitely counts as future work. But the one thing that I can say that we have is that although we're adding in numbers, we still have domain theoretic semantics. We're not moving outside that world, and we can still translate back into the original language in a way that preserves denotational semantics.